Once again, we welcome Dr. S. Mini Rani Madam, Associate Professor in Mathematics from NMI MS deemed to be University Mumbai to chair this session. Madam, please welcome. Now, Mr. Javed Masjid is a scholar, Department of Applied Sciences and Humanities, Faculty of Engineering and Technology, Jamia Millia Islamia, New Delhi, India. He will be presenting his paper. Yes, Mr. Javed Masjid, sir.
Respected dignitaries, audiences, and my dear colleagues, I wish all of you a good day. Myself, Javed Majid, a research scholar of Jamia Millia Islamia, pursuing PhD under the supervision of Professor M.I. Qureshi. I am going on this occasion. I am going to present my papers on generalizations of Nielsen integrals on this occasion of International Conference on Mathematical Advances and Applications. Today, first of all, I will give the outline of my paper. In this paper, I have generalized the Nielsen type of integrals and obtained the solutions of the integrals with the convergence condition through the hypergeometric approach using Gauss classical summation theorem and certain trigonometric relations. We also find some applications of the Nielsen type of integrals in the form of Weber and Egger type functions. First of all, in the introduction portion, I would like to define the first the Campbell simple alpha p, where alpha and p belongs to complex number, is defined by the relation alpha p is equal to gamma of alpha plus p divided by gamma of alpha is equal to this, given by 1.1, and the generalized hypergeometric form of 2f1 Gauss hypergeometric form. This is the generalized hypergeometric form p of q, where p and q denotes the number of numerator and the denominator parameters, where both alpha p and beta q and z are variables who take on complex values, where denominator parameters are neither negative nor zero. And this generalized hypergeometric function converges for all values of z less than infinity, where p is less than or equal to q, and q mod of z is less than 1 if p is equal to q plus 1, and diverges for z is not equal to 0 and p is greater than q plus 1, and absolutely converges for mod z is equal to 1, and if p is equal to q plus 1, where real part of omega is greater than 0, converges conditionally for mod z is equal to 1 and z is not equal to 1 if p is equal to q plus 1 and real part of omega is greater than minus 1 and less than equal to 0, and diverges for mod of z is equal to 1 if p is equal to q plus 1 and real part of omega is less than equal to minus 1, where omega is equal to the summation of denominator parameters minus the summation of numerator parameters. The hypergeometric forms of some elementary functions given by 1.4, and the Gauss classical summation theorem given by Gauss, defined by 2f1 alpha beta gamma 1 is equal to gamma of alpha minus beta, gamma minus alpha minus beta divided by gamma of gamma minus alpha, gamma of gamma minus beta, and 1 upon gamma of d is 2f1 a b d z is always defined for all real and complex values of d. And Srivastava and Dost defined the generalization of the Kempy-Different function given by Kempy-Different, the double hypergeometric function, and it is generalized by Srivastava Dost given by 1.8, and it reduces to the right function given by right if y tends to 0, and it reduces to the Kempy-Different function if all the real coefficients given in 1.9 are taken as unity. And for the convergence of the double hypergeometric given by Srivastava Dost, we should have delta 1 and delta 2 defined in 1.12 and 1.13 greater than 0. And if delta 1 and delta 2 are 0 and mod of x is less than rho 1 and mod of y is less than rho 2, where rho 1 is minimum of E1 and rho 2 is minimum of E2 defined in 1.10 and 1.11, and it diverges for x and y both equal to 0 and mod of delta 1 and delta 2 less than 0. And Cauchy's double series identities given by 1.14 and 1.15 and another two double series 1.16 and 1.17, which are absolutely convergent. And the Weber function given by H.F. Weber in 1879, known as the Lommel-Weber function, is defined by P mu of z is equal to 1 upon pi integral 0 to pi sine of mu theta minus z sine theta d theta, and the Anger function given by C.T. Anger in the year 1855, defined by J mu z is equal to 1 upon pi integral 0 to pi cos of mu theta minus z sine theta d theta. And in this present paper, we have defined some Nielsen type integrals as the generalization of the Nielsen integrals, where we have taken that the numerator parameters and the denominator parameters who do not are adjusted in such a way that the gamma function in the right hand sides are meaningful and well defined, and the results which do not make sense are tacitly excluded. Then the integral 0 to pi sine t raised power alpha cos t raised power beta e raised power iota gamma t is equal to this given by 2.1, where for convergence real part of alpha must be greater than minus 1, real part of beta greater than minus 1, real part of alpha plus beta greater than minus 2, and 2 minus alpha minus gamma minus beta minus gamma divided by 2 belongs to complex numbers excluding integers, negative integers, and 0. And another integral given by 2.2, the third integral 2 given by 2.3, the fourth integral where the integral ranges from 0 to 3 pi by 2 given by 2.4, and we have another integral 0 to 3 pi by 2 sine t raised power alpha cos t raised power beta cos of gamma t given by 2.5. So one more integral 0 to 3 pi by 2 sine t raised power alpha cos t raised power beta sine of gamma t dt given by 2.6, where for convergence alpha is greater than minus 1, beta is greater than minus 1, alpha plus beta is greater than minus 2, alpha plus beta plus gamma is not equal to 246, where alpha, beta, and gamma are all real numbers such that each gamma function in the right hand side of the equations above and 2.6 is well defined. Another one integral 0 to 2 pi sine t raised power alpha cos t raised power beta e raised power iota gamma t dt is given by 2.7, for convergence real part of alpha greater than minus 1, real part of beta greater than minus 1, real part of alpha plus beta greater than minus 2, 2 minus alpha minus beta minus gamma divided by 2 belongs to complex numbers excluding integers, negative integers, and 0. And another integral given by 2.8 and 2.9. And here we have given the proof of the integrals 2.1 and 2.2 and 2.3, that I1 is equal to 0 to pi sine t raised power alpha cos t raised power beta e raised power iota gamma t dt, that is further equal to integral 0 to pi e raised power iota t minus e raised power minus iota t divided by 2 I whole raised power alpha into e raised power iota t plus e raised power minus iota t divided by 2 whole raised power beta into e raised power iota gamma t dt, which on further becomes 1 upon 2 raised by alpha plus beta iota raised by alpha integral 0 to pi raised by iota alpha plus beta plus gamma into t 1 f0 minus alpha dash e raised by minus 2it 1 f0 minus beta dash minus e raised by minus 2it, which on further simplifying and using the equation 1.5, which we have already defined in the above equation 3.1, we arrived at the result 3.2. And after using the Gauss classical summation theorem 1.6 in equation 3.2, we get the result 2.1. And if we take all the numerator, all the parameters alpha, beta, and gamma as purely real, then we can equate real and imaginary parts. And on equating the real and imaginary parts, we arrived at the result 2.2 and 2.3. Similarly, we can prove the other results from 2.4 to 2.9 by following the same procedure. So we omit the details here, and we have obtained other integral as a special cases of the above integrals. If we take beta is equal to 0, we get in equation 2.1, we get the integral known as the Nielsen integral 4.1. Similarly, if we put beta is equal to 0 in 2.2, we get another Nielsen integral given by 4.2. And also, if we put beta is equal to 0 in 2.3, we get another Nielsen integral given by the equation 4.3. Similarly, if we put alpha is equal to 0 in 2.1, we get another integral given by 4.4 as a special case. And in equation 2.2 and 2.3, if we put alpha is equal to 0, we get equation 4.5 and integral 4.6. And if we put beta is equal to 0, we get the integral given by 4.7. If we put beta is equal to 0 in 2.5 and 2.6, we will get another integrals, the two integrals 4.8 and 4.9. And if we put alpha is equal to 0 in 2.4, we get the integral given by 4.10. And in equation 2.5 and 2.6, put alpha is equal to 0, we get the integrals 4.11 and 4.12. And if we put beta is equal to 0 in equation 2.7, we will get another integral 4.13. In equations 2.8 and 2.9, if we put beta is equal to 0, we get the integrals 4.14 and 4.15. And if we put alpha is equal to 0 in 2.7, we will get the integral given by 4.1716. And in equations 2.8 and 2.9, if we put alpha is equal to 0, we get the two more integrals given by 4.17 and 4.18. And lastly, we have obtained the applications of the above given integrals in the form of the Weber-Anger type functions. We have defined the first Weber type function e mu1 z given by equation 5.1. The second Weber type function e mu2 z given by 5.2. The third Weber type function as the application of the above integral e mu3 z given by 5.3, and e mu4z given by 5.4, e mu5z given by 5.5. All these Weber type functions are in the form of Shrivastava-Dost double hypergeometric functions. And another Anger type functions, we have also defined 5 types of the Anger type functions: j mu1z given by 5.6, j mu2z given by 5.7, j mu3z given by 5.8, j mu4z given by 5.9, j mu5z given by 5.10. And we have given here the proof of the Anger functions from 5.1 to 5.5. In these, we use the hypergeometric form of the sine function and the cos function. And after interchanging the summation and integration, the order of summation and integration, we arrive at the result of 5.12. And after using the equations 4.8 and 4.9, the already evaluated integrals in equation 5.112, we get this 5.13. And after using the double series identities given by Cauchy, 1.16 and 1.17 in equation 5.13, and further applying the definition of the generalized hypergeometric function and double hypergeometric function given by Shrivastava and Dost given in equation 1.8, we get the result 5.1. Similarly, we get the result of e mu2z to e mu5z. So we emit the details. Similarly, we can obtain the other integrals, Anger type integrals from 5.6 to 5.10 in the same way. So we emit the details. Lastly, on the conclusion, we conclude that these types of the integrals are capable of having the potential applications, some more potential applications in several fields of mathematical, physical, and engineering sciences, where we may consider some other definite integrals whose limit ranges from minus pi by 2 to pi by 2, 0 to pi by 2, minus pi by 2 to pi by 2. We have done the work in the paper Qureshi et al. And these are the references of my paper.
Now we request Ms. Sweta Shukla, research scholar, University of Allahabad, Prayagraj, Uttar Pradesh, to kindly present her paper. Madam, please.
I am a research scholar in Department of Statistics, University of Allahabad. Today I am here to present on the topic Spatial Data Outlier Detection Procedures. So first of all, what is a spatial data? Now anything which pertains to space or location is termed as spatial. Such type of data basically consists of two parts, that is the spatial part and the non-spatial part. The spatial part, it carries information about the spatial nature of the data, like what is the shape, what is the size, what is the location, basically the topology of the object. And the non-spatial part, it carries information about the behavioral aspects of the object, like what is the literacy, what is the employment in certain state, in certain country, in certain county, in certain district, etc. So altogether, spatial data is quite complex in nature, and thus it requires special attention when it comes to develop algorithms for the same. So it could be seen because of this complexity that none of the existing traditional outlier algorithms can be applied to it. So thus it poses a challenge to the researchers out there to come up with new approaches to deal such kind of problem. Apart from that, the other challenging aspect of this data type is the number of attributes, which might be single or multiple. Now, various methods are already available for the single attribute case, but since the complexity increases for the multiple attribute case, very few work has been done in this direction. Now, this paper aims in exploring this multiple multiple attribute case only. What happens in a multiple attribute case that we are introducing a multivariate structure in the spatial data. So it becomes a multivariate spatial data, and thus the complexity also increases. Now, when we are in a multivariate structure, we ought to have association between the objects. It might be similarity measures or the dissimilarity measures, but for all of this, a metric is needed. So here, a metric is defined as an equation 1, which is Mahalanobis distance, and there here x is the observation, c is the center, and v is the shape of the data. So conventionally, the C and V are replaced by the mean vector and the variance covariance matrices respectively. But since we are dealing with the problem of outlier detection methods, so this MD is needed to be robust, and for the obtaining robust MD, this C and V is needed to be estimated robustly. For that, various procedures are already available, but here this paper solely depends on one procedure that is given by comedian approach, which was introduced by Michael Farr in 1997 and was extended by Sajesh and Srinivasan. It uses median, which is a widely accepted robust measure for a random variable x. Like as in equation 2, we could see that median absolute deviation is defined. This is a robust alternative for the standard deviation. Also in equation 3, we can see that the comedian defined, this is the robust alternative for the covariance. Also, the robust alternative for the coefficient of correlation is defined as in equation 4. So for obtaining the multivariate analogs of this robust alternative previously obtained, this let us consider this matrix X, which is of order n cross p and consists of xi transpose rows and xj columns. Then the comedian matrix is defined as in 5, and the multivariate analog of this is defined as in 6. Now, apart from various advantages of the comedian approach, like the high robustness, the high breakdown value, there is a problem of non-positive definiteness. Now, in order for this MD to remain a metric, it is necessary that this matrix is positive definite. So, in order to sort this problem, transformations given by Marona and Zammer is being considered, where the multivariate correlation median matrix is decomposed into E lambda E transpose, where E is the matrix of eigenvectors and lambda is the diagonal matrix of the eigenvalues. Thus, these transformations are considered where M is this and yi is defined to be this. Then A new matrix Y of order n cross p is defined with these rows and these columns. Thereafter, the robust estimate for the center or the location and for the shape or the scatter matrices are obtained by this, where V is defined as this and gamma is defined as this. Also, a robust version of the Mahalanobis distance defined in equation 1 is defined as in equation 7. This is the robust version of it. Now, this robust MD thus obtained can be used as a test statistic T for a detection of outliers by this equation, that is the probability of T greater than CV is equals to alpha, where CV is this critical value and alpha is the level of significance. Here this chi-square P1 minus alpha is the 1 minus alpha-th quantile of the chi-square distribution with P degrees of freedom. Now, two algorithms have been proposed in this paper which are inspired by the algorithms given by Liu et al. In 2004. So for that, let us consider S as a set of n spatial units and F to be a set of P non-spatial attributes. Then F could be mapped from S to RP. Then any spatial objects like ith spatial object, its image under F can be viewed as like this. Next, let n be the set for the number of neighbors for each spatial unit. That is, ni is the number of neighbors for the ith spatial unit. Now, also for including the spatial character of the data set, what is needed is a neighborhood aggregation function. So let us say it is G, then it could be similarly mapped as F from S to RP. And the image of the ith spatial unit under G could be seen like this. Also, when this spatial character has been used, it is also needed to be explored the relationship between them. So for that, a weight matrix is needed where Wij is defined as 1 by n if I and j are the nth nearest neighbors and 0 otherwise. So if they are the first nearest neighbor, it is defined as 1, and if they are the second nearest neighbor, it is defined as 1 by 2, and so on. So the first proposed algorithm is the extended robust median algorithm. Here the aggregation function G is defined as this, where j varies from 1 to p, I varies from 1 to n. Wij is the weight associated for the ith and jth spatial unit, and S varies in the neighborhood of the ith spatial unit. Thereafter, a comparison function h for each I is calculated, which results in an n cross p matrix, and using that matrix, robust estimates of location and scatter matrices C and V are obtained. Thereafter, robust Mahalanobis distance is calculated using this equation and putting this C and V previously obtained. Now, any spatial unit SI is flagged as a spatial outlier if RMD SI is greater than CV. So in that case, that spatial entity would be classified as a spatial outlier. The second algorithm proposed is similar to the previous one, the only difference being in the aggregation function G, which is computed by using the concept of specialization indicator given by Nijkamp. Here is the aggregation function. It is calculated like this. And rest of the steps are similar, so it could be followed up. Thereafter, simulation study is being considered for the evaluation of algorithms, proposed algorithms. This equation 9 is used is the SAR model, spatial autoregressive model, and is being used for the generation of data. Here, W is a known spatial weight matrix, rho is the autocorrelation coefficient, and epsilon is a random error following normal 0 sigma square IN. Keeping in mind the restrictions of rho as in equation 10 and this These many sets are considered for 5,000 replications for 5% level of significance. For 5% level of significance for these many values of P. Also, the data is being contaminated by spatial outliers by considering 1/5 of the data to be contaminated by randomly choosing the spatial unit and accordingly adding contaminants randomly to the non-spatial attributes of the selected spatial unit. And if that non-spatial attribute happens to be positive, then a random error kept in the range of the selected column is subtracted from it, and if it is negative, then it is added to it. So this step ensures that the added contaminant is spatial and not a global outlier. The performance of the algorithms is measured in terms of type 1 and type 2 errors. Here it can be seen that these are the proposed algorithm, this and this, this and this. They outperform the existing algorithm, this and this, this and this for each P and for each N. Also, the computation time taken by the proposed algorithms is way far less than the existing algorithms for each P and for each N. So these proposed algorithms and the existing algorithms were applied to the real data, which was taken from National Crime Records Bureau, and it contained information 29 Indian states on 9 different variables. And these were the top 5 outliers detected for each of them, for each of the algorithm. It could be seen that Delhi was detected as a spatial outlier by both of the algorithms, while it was not detected as a spatial outlier in any of the existing algorithms, which is rare for a crime data set. So it was seen that the proposed algorithms agree while doing the empirical study as well. These are the references. Thank you. Any of the questions from the audiences are surely welcome. Thank you. Thank you for your time.
Now we request Mr. Mohit Sheikh, research scholar, University of Kalyani, West Bengal, to present his paper. Sir, please.
University of Kalyani, Nadia, West Bengal. My topic is dynamical description of central sets near and idempotent. Hilly Fustenberg first used the term central sets in topological dynamics. Let's start with filter. Let S be any set and U be any non-empty subset of S. U is said to be a filter on S if it satisfies the following properties. If A, B belongs to U, then A intersection B belongs to U. If A belongs to U and A is a subset of B is a subset of S, then B belongs to U and phi does not belongs to U. An alpha filter on S is a maximal filter on S. That is, an alpha filter is itself a filter on S which is not properly contained in any other filter on S. Let S be any set and let A be an element of S. Then A is a subset of S such that A belongs to A is said to be a principal alpha filter corresponding to A belongs to S. Let S be a discrete topological space. Beta S is equal to P such that P is an alpha filter on S. Given A is a subset of S, A bar is equal to P belongs to beta S such that A belongs to P. Then the set of all A bar such that A is a subset of S forms a basis for a topology on beta S. The topology of beta S is the topology that has these sets as a basis. This topology on the set of alpha filters is commonly known as the stone check compactification. where whenever we take S comma plus is a as a semi-group, we also assume that it has the discrete topology. We have defined minus x plus a in this way and p plus q this way. Beta S is a compact right topological semigroup. Now we introduce the concept of right ideal. A right ideal is a non-empty subset of a semigroup S comma plus such that I plus S. Similarly, left ideal if S belongs to I is a subset of I, and two-sided ideal if it is both right ideal and left ideal. L is minimal left ideal of S if and only if L is a left ideal of S, and whenever J is a left ideal of S and J is a subset of L, one has J is equal to L. Similarly, similar definition we can apply for minimal right ideal. An idempotent P is equal to P plus P in S is called a minimal idempotent if P belongs to a minimal left ideal. A smallest ideal is an ideal containing no ideal properly. Any housed up compact right topological semigroup S comma plus contains the smallest two-sided ideal Ks. Given a minimal left ideal L and a minimal right ideal R, L intersection R is a group. In particular, Ks contains an idempotent. An idempotent that belongs to K of S is called a minimal idempotent. The members of a minimal idempotence are of particular combinatorial interest. For more details, reader may consult section 2.2 of 2. Let S comma plus be a semigroup and let A is a subset of S, then A is called central in S plus. If there is some P, idempotent P in K beta S such that A belongs to P. In one, Hinman and Leader first introduced the semigroup consisting of alpha filters converging to zero. This definition, and Tutkavani and Vahed generalized this notion. Instead of zero, it is an idempotent. That is, the notion of the semigroup consisting of alpha filters converging to zero to an idempotent. Here we take R comma plus be a housed of semi-topological semigroup that is not necessarily commutative unless and otherwise stated. Here be the set of all idempotents in R, and for every x belongs to R. Tau x be the collection of all neighborhoods of x, where a set U is said to be a neighborhood of x if x belongs to interior of U in R. Customarily for a topological space X, XD represent the set X endowed with discrete topology. Here E star S equal to P belongs to beta S such that E belongs to intersection closure of A in R, where intersection is taken on A belongs to P. Now, synthetic set near E. A set is said, let S be a dense subsemi group of R comma plus and E belongs to R. A subset B of S is synthetic near E if and only for each U belongs to tau E. There exists some F belongs to P F U intersection S. What is the meaning of P F U intersection S? That is a set of all non-empty finite subsets of U intersection S. And some V belongs to tau E such that S intersection V is a subset of union of minus T plus B. T belongs to F. Let S be a dense subsemi group of R comma plus and E belongs to here. A set A is a subset of S is central set near E if and only if there is some idempotent P belongs to K of E star S with A belongs to P. As E star of S is a compact right topological semigroup which is proved in the paper of Tutkavan and Vahed, so it has the smallest two-sided ideal, that is K of E star S. Now, a dynamical system is nothing, a dynamical system X, T, S, S, nothing but a pair with X is a compact house of space, S is a semigroup, and for each S belongs to S, TS says that TS is a mapping from X to S, and continuous, and Ts is continuous, and for all S comma T belongs to S. Ts composition Tt is equal to St. Definition 0.15 x comma Ts be a dynamical system. We define theta is a mapping from x to x power x, that is the set of all functions from x to x with the product topology theta s equal to Ts. For each p belongs to beta s, let Tp is equal to theta tilde. Let x comma Ts s belongs to S be a dynamical system and define theta mass from x to xx by theta is equal to Ts. Then theta tilde is a continuous homomorphism from beta s onto the enveloping semigroup of x comma Ts s belongs to S, where theta tilde is the continuous extension of theta. For enveloping semigroup, see reference 2. As an immediate consequence of theorem 0.16, we have the following property. Tp composition Tq is equal to Tpq, and for each x belongs to S, Tpx equal to P limit Tsx, x belongs to S. Now, a uniform recurrent point near E, if and only for each neighborhood W of x, S belongs to S such that Ts belongs to W, and x y and y of x are proximal near E if and only for every neighborhood U of the diagonal in xx, and for each V belongs to tau. There exists S belongs to S intersection V such that Tsx, Tsy belongs to U. Let S be a dense subsemigroup of R, plus and E belongs to R. Let S x, Ts be a dynamical system, and let x, y belongs to X. Then x and y are proximal near E if and only there is some T belongs to E S star such that Tpx equal to Tpy. Now we use a lemma for a dynamical system x, Ts. The point x is uniformly recurrent point near E of x, Ts belongs to S. There exists U belongs to L such that Tux equal to X. Number C, there exists Y belongs to X and an idempotent U belongs to L such that Tuy is equal to X. And number D, there exists an idempotent U belongs to L such that Tux equal to X. A implies B, pick V belongs to L, and for each U belongs to tau X, X in X, let this set, then this Bu is a synthetic near E as X is uniformly recurrent. Therefore, we use the syntheticity near 0. We have, so for each U belongs to tau X and each W belongs to tau E, we pick TUW belongs to FUW such that this, and we set CUW this, and CU is equal to this, then this set has the finite intersection property. So pick Q belongs to star such that CU such that U belongs to tau X, a subset of Q, and we take U is equal to Q plus V. Since L is a left ideal of U star S, then U belongs to L. Now we show that TUX equal to X. Let U belongs to tau X. If we can show that BU belongs to U, then we are done. If possible, let BU does not belong to L, U, then this set, and CU belongs to Q, and if T belongs to U such that this and B belongs to tau X, B is a subset of U such that T is equal to TUW for some W, then minus T plus BV belongs to B, minus T plus BV is a subset of minus T plus B. A contradiction. For implication B to C, C to D, C proof of this, and D implies A. Let U belongs to tau X and X belongs to, let B is equal to this set. If possible, let B is not synthetic, then there exists W belongs to tau E such that this set has a finite intersection property. So pick some W belongs to ES star such that this is contained in W. We claim that E star S plus W intersection closure of beta is equal to pi. If not, then there are some V belongs to star S such that this. So one can get some T belongs to PFS intersection W such that minus T plus B belongs to W, a contradiction. Therefore, E S star plus W intersection closure of B is equal to 5. Let L is equal to E star S plus W, then L star is a left ideal of E star S. So L dash plus U is a left ideal of E star S, which is contained in L, and hence by millimeter of L dash plus U is equal to L. That's why I'm going to pick V belongs to L dash, such that V plus U is equal to U. By using remark 0.17, we have this, but this is a contradiction. We have another lemma, this proximality x and y proximal near E, then there is a minimal left ideal L of E star such that TUX equal to TUI. We have another lemma, U in K star is such that TUX equal to I if and only if both x and y are proximal near E and y is uniformly recurrent. Then we have the main theorem. This, let S be dense subsemi group of R plus and E belongs to R, also B is a subset of S, then B is central near E if and only if there exists a dynamical system x, Ts, Ts, S belongs to S, and there exists x, y belongs to X, and a neighborhood U of Y, such that X and Y are proximal near E, Y is uniformly recurrent near E, and B is equal to S belongs to S, such that Tx belongs to U. The proof is somewhat similar to the arguments of Hinman and Strauss in 2. This using characteristic function, this this this
Now we request Mr. Mukul Kumar, research scholar, ST College, Muzaffarnagar, Uttar Pradesh, India, to kindly present his paper. Yes, Mr. Mukul Kumarji.
Mukul Kumar, I present my research paper on the onset of thermosoluble convection of an elastic or viscous nanofluid in porous medium in presence of magnetic field. We discuss in this paper about the stability of the thermosoluble convection with magnetic field. Firstly, we define, we derive the a mathematical method. Uh, in this mathematical method, we derive the governing equation, which are equation number 1, equation number 2, equation number 3, equation number 4, equation number 5, 6, and 7 are the governing equation. Yeah. Equation number 6 is Maxwell equation, and equation number 8 and 9 are the boundary condition are given as below. Now we establish the non-dimensional variables given as in this slide: x star, y star, z star is equal to x, y, z over d and this. Now equation 1 to equation number 7 in reduce in non-dimensional form, we get equation number 10 to equation number 60. Now we use the basic state and its solution. The basic state of nanofluid is assumed and does not depend on the time and discussed as given follows: Q star U P W is equal to 0 and P star is equal to P of Z. It means P is a function of Z. Now T star is equal to T initial of Z, and E star is equal to phi initial of Z, and H, where H is the magnetic field of 0 1 0 0 1. The equation 10 to 14 with the boundary condition 8 and 9 gives the solution. Ti is equal to 1 minus Z, Ci is equal to 1 minus Z, and phi I is equal to Z. Equation number 10 to 14 solving with the boundary condition 8 and 9. We get this solution. Now we use the perturbation solution. We introduce small perturbation on the basic state for the investigate the stability of the system and write Q star is equal to Q basic plus Q perturbation, where Q dash is the perturbation. Similarly, T dash is equal to 1 minus Z is T basic state solution, and T dash is perturbations. Similarly, C dash, phi dash, P dash, and H are find out. Now next we reduce all these uh, we reduce all these equation uh, after the using perturbation. We get new equations 17 to 23, and the boundary conditions is 24 equation number. By now operating equation number 18 with the k into curl dot curl, we get in equation number 18 we operate curl twice curl into k, we get this equation, which is the next equations. Now using the normal mode analysis and disturbance is analyzed by normal mode analysis as follows: WTC phi is equal to WZ, theta Z, gamma Z, and phi Z, e raised to power ikx plus iky plus nt, where kx and ky are wave number. And using all these equations, we reduce new equation. Son, equation number 25, equation number 26, and equation number 27, equation number 28, and the boundary conditions in view of normal mode are equation number 20. Now we use the linear stability. The linear stability has a solution if and only if Ra, which is Rayleigh number, is equal to 1 upon this into this in equation number 13. The stationary convection for the stationary convection will be characterized by n is equal to 0 in equation number 30, and reduce it to in this equation number 31. In the known appearance of the Dufour and Soret parameter in equation number 31, we reduce to Rayleigh number in equation number 32. Now result and discussion. The equation number 32 express the stability stationary thermal Rayleigh number are computed as a function of solute Rayleigh number, nanoparticle Rayleigh number, modified diffusivity ratio, thermosoluble Lewis number, thermonanofluid Lewis number, and magnetic field. We observe that the nature of Rayleigh number with respect to Lewis number, Rayleigh number with respect to nanofluid Lewis number, Rayleigh number with respect to nanoparticle Rayleigh number, and Rayleigh number with respect to magnetic field, and Rayleigh number with respect to modified diffusivity ratio. In question number 32 gives this, which is del Ra over del Le less than equal, which is negative, and this this implies that if this quantity is negative, then we get a destabilizing mode, and if positive, we find the positive value, then we get a stabilizing mode. This implies that the stationary convection thermosoluble thermonanofluid Lewis number and magnetic field has stabilizing effect whenever Lewis number, modified diffusivity ratio, or nanoparticle Rayleigh number and solute Rayleigh number have a destabilizing effect. In figure 1 represent the Rayleigh number increase when magnetic field increase for different values of nanoparticle Rayleigh number. Rn is equal to 1, 5, 10 with the constant value of Na is equal to 5, Le is equal to 10, Rs is equal to 50, Ln is equal to 1000. The Rayleigh number Ra increase with the magnetic field Q, which implies that the on the stationary convection magnetic field has a stabilizing effect. In figure 2 represent the Rayleigh number decrease when nanoparticle Rayleigh number increase for the different values of magnetic field Q is equal to 1051 with a constant value of NALES RS LN. The Rayleigh number Ra decrease with the nanoparticle Rayleigh number, which implies that stationary convection nanoparticle Rayleigh number has destabilizing effect. In figure number 3, represent Rayleigh number decrease when the solutal Rayleigh number increase for different value of nanoparticle Rayleigh number Rn with the constant values of NALE, QNA. Ln. The Rayleigh number Ra decrease with the solute Rayleigh number, which implies that on the stationary convection solutal Rayleigh number has destabilizing effect. This is the figure number 3. Now in figure number 4, to represent the Rayleigh number and Rayleigh number with a thermosolutor Lewis number. In this figure, in this graph, Rayleigh, different values of nanoparticle Rayleigh number Rn with the constant values of NaRsQ Ln. The Rayleigh number Ra decrease with the solutal Rayleigh number, which implies that on the stationary convection of thermosolutal Lewis number has destabilizing effect. Now we find fifth graph, figure 5 represent the Rayleigh number decrease when modified diffusivity rates increase. In this graph, on the stationary convection modified diffusivity ratio have destabilizing effect. In sixth figure number 6, the Rayleigh number increase when thermo Lewis number increase different values of nano Rayleigh number Rn with a constant value of NaLeRs and Q. The Rayleigh number increase with the thermo device number, which implies that the stationary convection thermo-nanofluid device number has stabilizing effect. This is the figure. Now conclusion. On the onset of thermosoluble convection of an elastico-viscous nanofluid in porous medium in presence of magnetic field investigated by using linear stability, we drawn the main result as following. First, magnetic field and thermo or nanofluid device number have stabilizing effect for stationary convection. Second, the modified diffusive ratio device number nano Rayleigh number and solutal Rayleigh number have destabilizing effect for stationary convection. Third, the Walter model will be elastico-viscous nanofluid react similar to the regular nanofluid for stationary convection. Now last, these are some references, 14 references, and thank you.
We request Miss C.V. Sebastian, Assistant Professor, Government College, MG University Kottayam, Kerala, to present her paper. Madam, please.
I am Simi Sebastian from Mahatma Gandhi University, Kottayam, Kerala. Today, my presentation is about discrete Marsh-Rolkin pressure distribution. Sometimes it is impossible or inconvenient to measure the lifelength of a device in a continuous scale. In many practical situations, lifelengths are recorded on a discrete scale, such as number of years, months, cycles, etc. Hence, there is a need to find more flexible discrete distribution to fit various types of real data. The pressure distribution is one of the important probability distribution in extreme value theory. In 1927, French mathematician Maurice Fréchet has introduced the pressure distribution and is also known as type 2 extreme value distribution. This distribution has many applications and are listed in a recent book by Kotz and Nadaraj in 2000. A lifetime random variable x follows the continuous pressure distribution with the two parameters alpha and beta if its probability density function is given by equation 1. Recently, various generalizations of pressure distribution have developed in literature, and some of them are gamma extended pressure distribution, Kumarasamy pressure distribution, transmuted pressure distribution, etc. Marshall and Olkin in 1997 developed a technique to add more flexibility to the probability model by introducing a new parameter to the survival function of the Marshall-Olkin family of distributions and is given in equation 2. The PDF of the Marshall-Olkin family of distributions is given by equation 3. Krishna et al. 2013 developed the Marshall-Olkin pressure distribution with the survival function given by equation 4. In this paper, we propose a new distribution called discrete Marshall-Olkin pressure distribution, denoted by dm of delta p alpha, with the probability mass function given by equation 5, which is obtained using the method of discretization using survival function. The graph of the probability mass function of dm of distribution for different values of parameters are given in figure 2.1. Properties of the DMOF distribution are listed now. The probability generating function of DMOF distribution is given by equation 6, and mean and variance are given by equation 7 and 8. The survival function of the random variable following DMOF distribution is given in equation 9. And the survival function of continuous Marshall-Olkin distribution and discrete Marshall-Olkin distribution have identical at the integer points since they have the same functional form. The Hufford rate function of the DMOF distribution is given by equation 10. And figure 2.2 gives the shape of the Hufford rate function for different values of parameters. Now we consider the properties. Property 1, if x follows a continuous Marshall-Olkin distribution with parameters delta, beta and alpha, then y is equal to integer part of x follows a DMOF distribution with the parameters delta, p and alpha, where p is equal to e raised to minus beta raised to alpha. Property 2, if x is a non-negative random variable and c is a positive number, then y is equal to integer part of x raised to c follows DMOF with the parameters delta, p and alpha by c. If and only if x follows Marshall-Olkin pressure with the parameters delta, beta and alpha. In this section, parameters of the DMOF distribution are estimated using maximal likelihood method. The population moments are not in closed form, hence the method of moments failed to give estimates of the parameters. Now consider the maximal likelihood estimates, and the log likelihood function is given where n0 is the number of zeros in the sample and n plus 6 is the number of positive observations in the sample. Here, a real data set is fitted with the DMOF distribution using MLE method, and the data set is given in table 2.1, which represents the number of bits received by 126 US FAMEs that were targets of tenderofferts during the period 1978 to 1985. And the log likelihood function is given, and using chi-square, it is concluded that DMOF distribution is a good fit to the given data. Now we consider a particular case of the DMOF distribution when alpha is equal to 1, then the PMOF is given to reduces to equation 11 and is known as discrete pressure distribution. Then the estimates of the parameters are proposed using the method of different methods, method of proportion of zeros and ones, method of proportion of zeros and mean, method of moments, and MLE method. Here a simulation study is performed for the estimates of the parameters of discrete pressure distribution using the method of proportion of zeros and ones and using maximal likelihood method. Then table 2.2 gives the details obtained about the estimates of parameters using method of proportion of zeros and ones, and table 2.3 gives that by the method of moments. Then from table 2.2 and table 2.3, it is clear that as the sample size increases, standard error of the estimates decreases. Also, as sample size increases, estimated values of the parameters are very close to the true value. Hence, these estimates are good to fit the model. Also, standard error is less in estimation using method of proportions of zeros and ones compared to MLE method. Hence, method of proportion of zeros and ones is better method of estimation than MLE method in estimating parameters of discrete pressure distribution. Here, a data set is fitted with the discrete pressure distribution and a comparative study if done with the Poisson distribution using the method of chi-square. And it is observed that discrete pressure distribution is a good fit to the data compared to Poisson distribution. The conclusion of is in this paper, discrete Marshall-Rorkean pressure distribution is introduced and its important characteristics are studied. Parameters of the distribution are estimated by maximal likelihood method and application of the distribution is explored using a real data set. A particular case of the distribution called the discrete pressure distribution is studied and its important properties are studied. A simulation study is also conducted for evaluating performance of different estimates of the distribution. Some references are given in the slide. And thank you to all.
May I now request Dr. Khalil Ahmed, Assistant Professor, Department of Mathematics, to kindly present his paper. Sir, please.
My title of the presentation is The Study of Air Pollution Problem Using the Partial Differential Equations. This presentation gives details of study of air pollution problems using partial differential equations. This partial differential equation provides indication of distribution of pollutant quickly and cheaply than the monitoring networks, and helps to understand the mechanism of transport of atmospheric pollutant in an urban area. Let me start with the atmospheric diffusion equation using the Eulerian approach. The concentration of pollutants satisfies the continuity equation, which is in fact the partial differential equations, which is time derivative, advection, diffusion, chemical reaction, and the source term. And in this one, the most important the fluid properties are uj, which is the fluid velocity, and di, which is the molecular diffusivity. In addition to the fluid velocity, in addition to the continuity equation, the fluid velocity uj and the temperature T must satisfy the Navier-Stokes and the energy equation respectively. That means we need to solve coupled equation of mass, the continuity, momentum, and energy equation. But the pollutant occurs in the atmosphere at parts per million concentration. So therefore, the pollutant do not affect the meteorology. So therefore, the equation of continuity can be solved independently of the coupled equation. So the complete description of the pollutant behavior rests with the solution of equation of continuity. That is what the atmospheric diffusion equation. But the flow of interest, that is our atmosphere, is not laminar, but it is turbulent. That means it is irregular and random. So therefore, we decompose the fluid velocity into the deterministic mean component and stochastic, that is perturbation component. Substituting uj this in the continuity equation, the diffusion equation or the equation of continuity or the partial differential equation is this. Since uj is random, therefore ci is also random. Therefore, we must decompose ci again into two components, which is ensemble average and the stochastic component. And again, we substitute ci this into the atmospheric equation. Then we have this. But the problem here is that we have here more dependent variable than the equations. So which is called a closure problem of the turbulence. So we need to close it. So to close it, we require additional equation. So these additional equations gives again new dependent variable, and this process goes on. And we need to stop it. That means we need to close it. So we close that process, and for that we assume that the turbulent fluid has eddies of the fluid, and the turbulent fluxes, that is this and this, and the concentration. So we are what we call connecting these two, and this two we are connecting by mixing length or K theory. So assuming that this turbulent flux is, in the fixed law case. So here Jk is 1, 2, 3, and leaving the non-diagonal component, which is 0, and we take only the diagonal element, then uj can be approximated this. And this technique is called first order closure, and also it is called K theory. In addition to this closing the equation, we assume that the molecular diffusion is negligible compared with the turbulent diffusion. So therefore, this can be neglected. And the atmosphere is incompressible, therefore it is 0. And we consider the chemically inert pollutant, therefore Ri is 0. Under these assumptions, the atmospheric diffusion equation becomes this. So, which can be expanded with the I, that is the X, Y, and Z component. And we have, this is the what we call expanded atmospheric diffusion equation, which predicts the spatial as well as the time variation concentration of C with the initial and boundary conditions. And further, we assume, that is, we align the x-axis in the direction of the actual wind, that is east, the y-axis align along the crosswind direction, that is north-south, and z-axis vertically upwards. And then the pollutant concentration does not vary in the crosswind direction, therefore this can be 0. Therefore, we can consider it as purely a two-dimensional. And horizontal advection is greater than the horizontal diffusion, so therefore this can be neglected. And the vertical diffusion is greater than the vertical advection, and we are considering the short-term air quality, that is hourly or daily. Therefore, we consider as time dependent. So under all these assumptions, the atmospheric diffusion equation becomes delta C by delta T plus U of Z delta C by delta X, delta Z delta by delta Z, Az delta C by delta Z, which is in fact a partial differential equation, and which is also called a mathematical model. So this C is function of xzt. And to study the air pollution problems, we are considering two what you call boundary layers. One is the planetary boundary layer, or also it is called mixing height or mixing depth, which is extend to up to 1 to 1.5 kilometer, where the pollutant released from the surface, that is the ground, may get mixed and do not rise. And within the planetary boundary layer, we have a surface layer which is extending up to 50 to 100 meter. So where the eddy transport of heat, water vapor, viscous stress are constant. So applying the initial and boundary conditions. So initially the concentration will be 0 at T0, and for the desired distance, we are calculating the concentration in the horizontal direction, and this is the vertical height. And the boundary condition, that is at x is equal to 0, that is the left boundary condition. The concentration of pollutant is Cv, that is for 0 to h, and for all t greater than 0. And this is the emission at the ground, and this is constant, emitting at the constant rate, that is up to the city limit. And beyond this L, and then up to the desired distance, this Q is 0. And we study the concentration of pollutant from 0 to capital L. And note that from 0 to L only, we have a we call emission, that is the city limit, and this capital L is a downwind, that is beyond the city limit we go. And there is a mixing height where the pollutant will not be escaping. So the delta C by delta Z is 0 at Z equal to H. So this is the upper boundary condition. So if you have a look at the physical layout of the model, here, that is what the crosswind, and this is the wind direction, that is X. This is the vertical direction, and we have this is the left boundary condition, and from 0 to L, we have a what you call the emission rate, and we study the pollutant distributed concentration of pollutants from here to desired distance. We go up to the capital L here. So this is the physical layout of the model. Of course, in this particular model, I have not considered the leakage velocity. That is, some of the pollutant are escaped in the atmosphere, and the pollutant undergoes the chemical reaction, and some of the pollutant are washed out because of the rain, and some of the pollutant are what you call washed out by the clouds, that is rain out, and some of the heavy particles pollutant are deposited at the ground. So these are all the removal mechanism we have not considered here. We have only considered the not removal mechanism and non-reactive pollutant. So these are the two important parameters which are in fact the input to the model, I mean partial differential equation. So here we are considering two cases, that is the neutral and stable condition, which are not good for the air pollution point of view. And in fact, the stable happens during after the sunset till the sunrise, and neutral condition is just before the sun rise and just after the sunset. So it is a very what you call very for small time, but this is the major what you call atmospheric stability condition, which is not good for air pollution. So this U and Kz, which are the function of Z, which are the very important input to the model, and the profiles have been considered here. For eddy diffusivity, this is for the neutral case, and this is for the stable case. And the wind velocity So this is what you call the surface layer, and this is the planetary boundary layer. So we have a power law and a logarithmic law and power law, and this is for the neutral, and this is for the stable condition. So these are all experimentally found, and this which is a function of z, and this has been going to into the partial differential equation as the input. And as far as the solving of partial differential equation, so since u and kz are a function of height, that is z, therefore we cannot use analytical method. So therefore we have used the numerical method. And here we have used Crank-Nicolson finite difference scheme. And the finite difference scheme, of course, there are finite volume, finite element, but finite difference is very simple and powerful for all fluid flow problem. And whenever you are dealing with regular geometries, and since it is, and here for time derivative, I have used the forward difference, which is the second order correct. And for attraction, upwind difference, which is transportive and conservative, and it is numerically stable. And for the diffusion term, central difference, which is of second order. So the finite difference scheme, what we have used is numerically stable, consistent, and convergent. And when we substitute when I discretize, and we get a tridiagonal matrix. And this tridiagonal matrix can be solved by a Thomas algorithm, which is very, very efficient on the computer, and it gives the round of error stable. The round of will be stable here. And since it is a time-dependent model, so therefore we need to specify the condition for steady state, and the steady state is reached when the difference between the concentration at one time level to another time level is 10⁻⁻⁵. And the code which is written to solve this partial differential equation along with the numerical method. So we need to do the verification of the code, and that is done with the consistent and the stable numerical scheme. That is what the Crank-Nicolson scheme. And we did the convergence study by residue fall, and also grid independent analysis. And the ambient air concentration of pollutant has been obtained for stable and neutral atmospheric stability condition, but unstable is not, I mean, it is good for air pollution because unstable conditions mixes the pollutants in the atmosphere, and thereby it reduces the effect of air pollution. And for pollution point of view, stable is not a good condition. So these are the ground level concentration at 2 meter height, and if we see in the stable case, the this is the 6 kilometer, that is the city limit, and we calculate the concentration of pollutant at up to 12 kilometer. And as we see that till 6 kilometer we have emission, so therefore under the stable condition, which is not good for air pollution, and therefore the concentration of pollutant is reaching to 250 microgram per second, I mean microgram meter square, and beyond limit it is decreasing, but still till 12 kilometer it is still around 11 microgram per. But if you look at the neutral case, the concentration is reaching to the maximum 70, and beyond that up to 12 kilometer, it is less than 20 or 15. So that means this is the case, what you call, which is not good for air pollution problems. And here are some more example, graphs for different height for 3 meter, that is 3 meter, 9, 3 and 6 and 9 feet meter height. That is the concentration of this is these two are for 2 meter, and this is for 369 and 369 for the neutral and the stable conditions. And these are the what you call literatures or references where the atmospheric chemistry and the physics of air pollution. This is the, I mean, and for atmospheric diffusion, this is the book Pascal and Smith. And for all numerical thing, the computational fluid dynamic and the fundamental of fluid. These are the for the numerical study, and this is for the meteorology and all that. So thank you one and all. And if you have any questions, you can ask me. Thank you. Thank you all.
Now we request Dr. Jayanta Biswas, Assistant Professor, Sri Vishwakarma Skill University, Haryana, to present his paper. Kindly, sir.
Good afternoon, everyone. I am Jayant Bishwas from Vishwakarma Skill University, working as an assistant professor in Department of Mathematics and Statistics. Today, I'm going to present my article entitled as on okay. Good afternoon, everyone. My name is Jayant Bishwas from Sri Vishwakarma Skill University, working as an assistant professor in Department of Mathematics and Statistics. Today, I'm going to present my article on R delta open sets in ideal topological space is an implication on COVID-19. This paper was written by myself and my mentor, Dr. Prasannan. We have divided these presentations into 6 major parts. First is overview of the article, literature review. Second one is introduction and topological property of R delta I open sets. Third is general idea of R delta I supercontinuous functions, then implications of functions on COVID-19 data. And in the end, we are giving some important references which we have used throughout this article. First, in the overview, this article mainly focuses on relating R theta supercontinuous functions and Ri continuous functions in topological sense, as they share a lot of similar properties. This led us to develop and study different class of sets which are introduced in this article. Although some of the sets are used and have been defined in this article, further sets were defined in other articles which we have published in some peer-reviewed journals and Scopus Index journals. Then we also study the basic properties and place them in the hierarchy of strong variants of different sets. have been established. We also applied maximal open set and topological ideal, which help us to generate new topological space from the original ones with the help of the new ideal I. Furthermore, we applied these peculiar and interesting sets to define upper and lower approximate functions. These lower and upper approximate functions helps us to check the accuracy of the COVID-19 data in Haryana. Now, we move on to the literature review. Just before we start anything, we should know some basic knowledge. That is what we mean by ideal, what we mean by ideal topological space, and what is the basis of these topological spaces. Again, we will also learn about approximated topological spaces also, which we will discuss during the slide. First of all, we should tell you what we mean by ideal. An ideal is a non-empty subset of power set of X, which satisfies these two properties. That is, if A is in is a member of I and B is a subset of A, then B has to be a member of I. Now, if A and B are member of I, then their union will also lie in that ideal. Therefore, if a subset of powers of X satisfy these two properties, then we call that subset as ideal. Now, what we mean by ideal topological space? Ideal topological space means the triplet X, their topology tau, and the ideal I. With the help of this I, Jankovic defined CL star of A, which you can go through the literatures. I'm just giving you a hint how he had defined CL star A and all. Now, basis of a topology, let X tau be a topological space and I be an ideal on X, then the collection beta B is equals to open set intersection ideal, where open set is always a member of topology and I1 is a member of ideal. Sorry, is a and this forms a base for a new topology called tau star I. In short, we also call it as star topology on X. Now, we should define some other important open sets in ideal topological spaces, that is regular I open and delta I open sets. To define regular I open, I will recall the definition of regular open sets. When we call a set A to be regular open, if interior closure of A is equals to A, then we call that set regular open. In the similar fashion, we have defined this regular I open. That is, if interior closure star of A is equals to A, then we call that set A as Ri open set. Now we will define delta I open sets. Just to define that delta I open set, we should know what is delta I closed sets. And now this has to be related to delta I cluster point. So point X is said to be delta I cluster of a set S if S minus interior closure star of U is non-empty, where U is the open neighborhood of X. Now, when we collect all these delta I cluster points, it forms a new subset, which contains the set S, and uh, it it is a larger part. It can be seen as the closed sets, like a collection of all cluster point forms the closed set. In the similar way, it can be seen as delta I closed sets of a set S. When we call a set A to be delta I closed, when S of delta I A of delta I is equals to A. Then we call that set A to be delta I closed set. And then we know the implication that the complement of delta I closed set is delta I open. Now let's move to the important definitions which we have defined. Basically, the general idea of R delta I open sets in ideal topological space. An open subset U of a space X is called R delta I open if for each X in U there exists a delta I closed set CX such that X belongs to CX and CX is contained in U. Then U is said to be R delta I open. So basically, R delta I open is union of delta I closed sets. Now, how we have defined R delta I open? This is also basically an I open set, which is a union of delta I closed sets. So formally, we should define it as an open set V of a space X is called R delta I open if for each X in V there exists a delta I closed set CX such that X belongs to CX and CX is contained in V. Again, we can easily verify it. Now, the topological properties of R delta I open set. This is beautifully constructed in this table form. We have given all the proofs in our article, and we also give sufficient amount of examples which shows that the converse path or the reverse implication are not true. For examples, please go to my work and you will find in the beautiful examples which we have calculated and which we have constructed with the help of counter examples in general topology book, and there are plenty of examples which shows that the converse part may not be true. Now, overview of R delta I supercontinuous. That is the general idea of this supercontinuous function, how we are going to define it. A function f from a topological space X into a topological space Y is said to be R delta I supercontinuous at a point X and X if for each open set V containing fx there exists an R delta I open set U which contains X such that f of U is contained in V. The function f is said to be R delta I supercontinuous on X if it is true for each X in X. I think that's clear enough. Now we are defining how to construct R delta I supercontinuous function. A function f from a topological space X to a topological space Y is said to be R delta I supercontinuous at a point X in X if for each fx if for each open set V containing fx there exists an R delta I open set U such that f of U is contained in V. The function f is said to be R delta I supercontinuous on X if it is R delta I supercontinuous at each X in X. Now, the implication of functions in data of COVID-19. Basically, we check the accuracy of the data just to verify how much the data is relevant and how much data is true. We have checked with the help of this new open sets which we have defined. Before we check the accuracy, we should understand what we mean by R delta I accuracy, what we mean by R delta I lower approximation, R delta I upper approximation, boundary delta I, and positive reason delta I, negative region delta I. So we should consider a topologized approximation space, which is basically a combination, a triplet which contains a non-empty set X, a relation R, and topology tau. Here we are talking about ideal topological space, so we should also consider an ideal I on X and a which is subset of X. Basically, we will define all this R delta I lower approximation, R delta I upper approximation, R delta I positive region, R delta I boundary region, R delta I negative region, and R delta I accuracy. For that, we need a subset A, which is non-empty. So, how we define lower approximation? R delta I, which is defined as union of all those uh, delta I opens such that all those delta I open is contained in the set A, right? Now we are defining upper R delta I approximation of A by taking all those delta I closed sets, taking intersection of all those delta I closed sets such that those R delta I closed sets contains the set A. Now, boundary is clear enough. That is upper approximation minus lower approximation. Positive region is equals to the lower approximation of A, and the negative region is equals to X minus the upper approximation of A. Now, the important part which we have used in our article is this R delta I accuracy. So how we are defining this R delta I accuracy? This is basically the ratio of lower divided by the upper approximation, where upper approximation cannot be zero, and here we have defined it. Now, let me disappoint you a little bit. We have not given the data of COVID-19 of Haryana because it was too huge to handle in this PPT. Therefore, we have applied those data on a chemical reaction which has these five attributes, basically five different amino acids and their quantitative attributes on it. So these are A1, A2, A3, A4, and A5 are five amino acids, and X1, X2, X3, X4, X5 are five attributes. Okay. So again, topologize approximation space near reflexive relation. So here we have defined five reflexive relations, which is defined as follows. That is Rk is equals to pair of xi xj such that xi of ak minus xj of ak is less than the standard deviation of kth row divided by 2. And hence we have found this right neighborhoods of five reflexive relations, which are as follows. And as soon we get this, it was easier for us to calculate the lower approximation and the upper approximations. And as soon we calculate their lower approximation and upper approximation, then we can calculate the accuracy, and with the help of that accuracy we can check how much our data is correct. How much correct data is correct, and in the similar way we have checked how much our data of COVID-19 in Haryana was correct and how much it is accurate. So these are some important references which we have used throughout the article, and especially Donchev and Al Omari has worked a lot of has beautiful work in ideal topological space, and I will recommend that you should go through these papers and find out some new and interesting things about ideal topological space. And in the end, thank you very much for your support. Have a good day.
Thank you very much. I thank each and everyone for presenting the paper. Now we shall move on for interaction. Kindly click the interaction or discussion live in Zoom button just below this, and you will be taken to the Zoom. Chairperson will interact, and the other paper presenters can also clarify their doubts if any, and we as organizers will also announce